Good morning. Welcome to NGSS Physics. We are going to be going over projectile motions today. So grab a pencil, a piece of paper. Your formula sheet would be good if you're making your own or if you have the formula sheet that I gave you. One of those would be a really good idea to grab, maybe even a calculator, so that you can calculate along with the problems that we're going to do with projectile motion. First off, what is projectile motion? So far, we've only really been going over motion in one direction. And it's either been at a constant speed or velocity, or it's been at an accelerated velocity. And we did some practice problems with those. Well, we are going to use both of those today. The one with constant velocity and one with accelerated velocity. And we're going to put them together. When we do that, we have actually the components to solve projectile motion problems. They're two-dimensional motion problems. What am I talking about with a projectile? I'm really talking about something like, a cannonball or a bullet that's fired, an arrow that's shot, or anything that's near the Earth's surface. So it's got two directions. It's going in a forward direction, and at the same time, it's falling down to the ground. So it's in free fall. So there's two different components, the forward and then the downward, the falling direction. Both of those things are going to be a part of this problem. We're going to call the horizontal velocity, that's the part where it's fired and going straight, that's going to be horizontal. And this velocity is going to be kept constant, so we can use the plain old basic velocity formula for that. And then there's going to be a vertical velocity, and this is the part that's falling down, going down. And because the force of gravity keeps pulling on it, this is going to be accelerated. And so we're going to have to use one of the formulas with acceleration in it. And for our purposes, the master equation works really, really well. Now, obviously, near the surface of the Earth, there's a lot of air and air resistance. We're going to go ahead and ignore that. We're not going to take into account the forces of air resistance in our problems today, because it's going to be such a small number, it's not going to really affect our calculations. Okay, let's break that up into the two pieces. What do I mean by the horizontal component? Well, if we imagine a cannonball being fired, you know that the cannonball is shot in a certain direction, straight like this. That would be the horizontal component. And the horizontal component follows Newton's laws. And Newton's very first law says that an object in motion stays in motion unless an outside force acts on it. So if we only had the horizontal component and that cannonball was shot, then it would keep going forever and ever at the same exact speed if there were no other forces acting on it. That's Newton's first law. So the horizontal component for velocity, we could just use the basic velocity formula to solve equations for the horizontal. Now, the other component is called the vertical component. Now, imagine if the cannonball just rolled out of the cannon, it would fall straight down to the ground. And the reason why it would do that is because there's a force in the earth called the force of gravity pulling everything downward. This is also following Newton's laws of motion. This happens to be Newton's second law of motion. Okay. Now you've got a force acting on it, and that force changes its motion. And because the force never lets up, it's constantly acting on the cannonball, this is accelerated motion. So here we're going to have to use one of those formulas with acceleration in it. And for our purposes, the master equation works out really well, mainly because all of those other equations are based on the master equation. But when you fire a cannonball out of a cannon, you don't just get the vertical component or the horizontal component acting separately. They are actually acting together at the same time, simultaneously. You've got the horizontal component over here, which is behaving with Newton's first law of motion, and it's got a constant velocity. And you've got the vertical component down here, in which it's falling at an accelerated rate because the force of gravity keeps pulling on it constantly. And the cannonball doesn't follow either of those paths. It really follows this parabola, this curved path right here. The question is, okay, we can do calculations for the horizontal, we could do calculations for the vertical, But can we do calculations to figure that out? And the answer is yes, we can. And this is how we're going to do it. Cute. Okay, so to solve projectile motion problems, all we need to do is separate the math into two smaller one-dimensional problems. We need to have a horizontal component and a vertical component, and we'll use a separate equation for both of those components. And they're, because it's the same cannonball being shot, they're actually related by time. So what we're going to do is we're going to first figure out how much time that cannonball is going to be in the air. The easiest way to do that is to solve for how long it takes to fall, because we know a few things. We know that the acceleration is due to gravity, and we know what that number is already, 9.8 meters per second squared. So if we solve for the vertical component, time, we also know that the time it takes to fall is the same amount of time it's going to be flying straight through the air in the forward direction. So then we can use it in the regular velocity formula to solve for the second component. Each direction, horizontal and vertical, they obey Newton's laws of motion. So therefore, they also obey all of those equations of motion, because that's where the equations come from. Here's the vertical component going down. Which formula will we use? Well, we're going to use this one, the master equation. Notice that in the master equation, we have that acceleration. Remember, that acceleration is going to be due to gravity. This is in free fall. And so the force acting on it is gravity. And so that acceleration is going to be, 9.8 meters per second squared. If you want to put a direction on it, you can put a negative 9.8 meters per second squared. We also know that if it starts at the cannon, it wasn't falling at the beginning, and it suddenly is starting to fall, so that VI is actually 0. So we can eliminate it from the equation. I can go ahead and exit out up here, okay? So that the equation actually looks like this. I can put in a G for A, and I can put in X out the VIT part of it. Now, if you wanted to, you could go ahead and put in negative 9.8 for the G, and then you could go ahead and divide it by 2. So you could do this. You could say, oh, X is really equal to negative 4.9 T squared. You could do that. Just go ahead and put in the 9.8 into G and then divide it by 2, and it makes it a little bit simpler if you wanted to. Eventually, though, we need to solve for T. So we need to multiply by 2 on each side, divide by G. Remember, this down here is actually G, okay? And square root it. Now, if you do it the simple way over here, you could just say, oh, X divided by 4.9, oops, and then square root it. So you could do that if you wanted to, okay? And that makes it a little bit simpler. If you want to write this down on your formula sheet, you can do that. But remember, this is only when something is falling on Earth, okay? If it's falling on a different planet, then the acceleration is not 9.8 meters per second squared. But when it's falling on Earth, you could solve for T using that. So you can eliminate some of the things that you have on there. And so all you have to do is plug in the distance that it falls. That's the vertical component. Once you solve for T, okay, you know how long it takes to fall. That same amount of time is how long it's going to be traveling in the horizontal direction. And so we could use the basic velocity formula to solve for the variables there, okay? There's the basic velocity formula. And right below it, you could see I solved for displacement instead, but it's still the same exact formula. The key is now we have the time, because we just figured out how much time it takes to fall on the last slide. Let's take a look at a problem and put it all together. An airplane is flying at a certain speed, 115 meters per second, and it drops a bundle to the ground. If the airplane is 1,050 meters high, how far does the bundle go before hitting the ground? Perfect. We want to know what's the forward throw distance here? How far does it go before it hits the ground? First off, we need to know how long it takes to fall. Because once we know that, we could use that speed to figure out how far it will go. So let's break it down into our two pieces. Here's that airplane, and we know that it was 1,050 meters high. So I take my vertical formula. We know that it's accelerated velocity, so I'm going to use the master equation. Remember, VI is 0, X is negative 1050, and the acceleration is 9.8 meters per second. I can eliminate the VIT because this right here is 0, so that gets eliminated. And then I get the formula like that. So I solve for t. There it is. Or you could do that shortcut that I gave you where you have 4.9, x over 4.9 in there. You can use that if you want. Okay. Plug those numbers in. 1050 meters for the top, x, and 9.8 meters per second squared for the bottom, a, just like that. And you should get 14.6 seconds. That's how long it takes to fall. So if the plane wasn't moving at all and they just dropped the box out of the window, it's suspended in the air, it would take 14.6 seconds to fall to the ground. Well, as it's falling to the ground, it's actually moving forward. It's moving forward at a speed of 115 meters per second. So next, I'm going to do this part, okay? It's going to be traveling at that speed for that time that we just calculated, and I want to solve for how long it's going to go, so I have to manipulate the formula to look like this. Okay, all I did was multiply by t on each side, and then plug in the numbers. Notice that this is the one I calculated on the previous slide. The 115 was given in the question. And so I figure out that, it's going to go 1,679 meters before it hits the ground. And that's it. That's how you would do that. So projectile motion in 2 dimensions, okay? You could very easily solve them if you break down the question into 2 separate parts, a horizontal component and a vertical component. And remember, both those parts follow Newton's laws. The vertical component, it's being accelerated due to gravity. So you have to use a formula with acceleration in it. The horizontal, it's constant velocity. What do they have in common? How long they are moving through the air. The time it takes to fall to the ground is the same amount of time that it's going to be flying horizontally through the air. So that's what they both have in common right there. That's the key. Time is the same for both of them. It's an equal amount of time to fall as it is flying the horizontal direction. Remember, when it starts to fall, it started from 0. And so you can simplify your master equation down very, very nicely. Here, with the horizontal, the velocity is constant. It's not accelerated motion. So all we need to do is use that very basic equation that looks like this. Okay? And because the vertical component is accelerated, we need to use the master equation in one of those variations that you saw. And the best way is because it starts with a velocity of 0 in its fall using the master equation that looks like this, okay, for that side right there. Alrighty, this concludes the projectile motions lesson. Thanks for listening. We'll see you guys later.